Okay folks, now we're going to take a look at the diode and actually start putting some currents across it in terms of applying a voltage and generating currents. There's a couple images to start today. First one is pretty obvious here. It's a diode, right? And so the key thing I want you to remember that the basic definition of this component is that it's rectifying, meaning that it has a large current in one polarity of voltage and a very small current in the other polarity. And we'll discover more about how that works here today. And it's also important to remember that just a plain old diode can do some pretty amazing things. So this device here, that's just a forward bias diode, and we'll get to that when we talk about optoelectronics. Also in optoelectronics, diodes are used as are used often for solar cells, but also for photoreceivers, for basically taking a fiber optic signal and converting it back to an electrical signal. And so these are all important topics, and what we discuss today is going to be critically important. So let's go back for a little bit of review. And last time we basically talked about a diode where there is no voltage applied. So here I have a PN junction. Here's my P side and N side. And I cut the wire here, meaning that I've got no voltage on this thing. So I'm just letting this sit on a table. And we said, well, obviously, if you have just a diode sitting on a table, there's no net current, right? It's not going to generate current over time. And so we said that we could use that to say that the drift and the diffusion currents moving across the diode must be equal to zero. They must add up to zero, and that's both for the electrons and for the holes. And so there's no net current. And we also looked at this in terms of what makes up drift current and what makes up diffusion current. The main point that we want to remember for this is that here's my diode, right? We had diffusion of carriers that then created an electric field and a contact potential. That contact potential shifted the bands such that the Fermi levels line up. Okay? There's my contact potential. And as a result, my currents changed as follows. The first thing I have in terms of the current components, as a review, is I have drift current. I have drift current which is composed of minority carrier generation near the junction. When I say near, I mean within roughly a diffusion length. And so what this says, if I am on the P side here, I have electrons which are thermally generated. An electron comes up from the valence band to the conduction band, and if it is within a diffusion length of the edge, it can wiggle around and then slide down here via electric field, which is drift current. And the reason why it has to be roughly within the diffusion length of the edge is we said earlier, diffusion length is roughly how far a electron or hole will go until it recombines. So if it comes up way out here, it's not within the diffusion length. It might try to move in this direction, but it will recombine back to the valence band before it gets to the edge of the depletion region. And so again, what we care about is minority carrier generation. Minority meaning there's few electrons compared to the majority, which is holes. Within the diffusion length of the edge of the depletion region, it experiences the electric field and it gets swept across. We have the same thing for holes over here. An electron's thermally generated, which is the same as thermally generating a hole. If it's within a diffusion length of the edge of the depletion region, it can be drifted across as well. This current is also very small because up here on the P side, we don't have that many electrons, right? You doped at P-type, and all these excess holes kill off and reduce the electron population. Same thing for the holes on this side. This is N-type material, and so all those extra electrons kill off most of the holes by recombination, so you don't have many holes that can go back across here. And then we said the other type of current we had going on all the time for this device was diffusion current. We have a very high concentration of electrons on this side, right? Very high concentration. But the problem is that if they are below, down at energy levels below the contact potential, they can't get over this barrier here. This is an energy barrier, right? And so only the electrons which find themselves up here, higher than the energy of the energy barrier, will then be able to diffuse across from the high concentration on this side to the low concentration on the other side. And so that'll become important today because we'll look at, to know, if you want to know how many electrons are up here at this higher energy, well, it's simple. We already created a function earlier this semester for understanding what electrons exist at what energies. And we have the same thing for holes as well, to understand how many holes get enough energy to make it over the barrier and diffuse to the other side. So let's take a closer look at both of these. So the first thing we're going to do is we're going to put forward bias on this thing. And so look what happens here. I put a positive voltage on the P side for forward biasing a diode. And the first thing you'll notice is that the depletion region is now smaller than it was on the previous slide, which means I have a smaller contact potential. That should make complete sense, because if you look at my contact potential, I've got negative voltage here, positive here. The applied voltage is opposite to that. And so it's like having plus minus, it's like having, plus 3 volts and, well, contact potential is smaller than that. Let's say that the contact potential is 1 volt and we apply 0.5 volts here, then you would have 1 volt minus this for a net voltage drop of only 0.5 volts. And so this is in the opposite direction as this voltage, and therefore it gets subtracted from it. And as you subtract that, you have less contact potential here. And if you have less contact potential, you must have less charge dopants here contributing to that contact potential. So, the question is next, how does this change my band diagram? Well, if I reduce my contact potential by putting a forward bias here, I put positive voltage on this side. Positive voltage shifts the bands down, which is the same as shifting the bands up on this side. And you can see that now the Fermi levels no longer line up because this is shifted down. And so what's this going to do to my currents? Well, the first thing is the drift current will not change. I still have a slope here, right? And so every minority carrier electron that's generated right at the depletion edge will go across, and those that are near it within a diffusion length will have a good chance of moving around before they recombine and drift across as well. Same for holes. Thermally generated hole, electron goes up. I have a hole. That hole can move around and it can go across. My analogy I use for this, which I think is helpful, is, I'll draw it here even. Let's say there's a chair or a stool here, and here I am, and I'm an electron and I'm dancing around. And if I dance around on this thing and I have 1 foot fall off on this side, then I will fall to the ground every time, right? I'm not going to be able to levitate back up in the air. And so my probability of going off the stool is 100% if I start to basically see the energy capability to fall off the stool into the ground. Okay? And so you say, well, does that probability change if I make it not a stool, but let's say it's the top of Baldwin Hall, and here's the quad out here? Well, no, it's the same thing. Even though the total energy drop here is increased, as soon as I take 1 step off here, my chances of morbidly ending up on the ground in the quad in Baldwin are the exact same as they were to fall off a chair. And so that's a key point to remember for drift and diffusion current. Let me erase this here. For drift current, is that even though the barrier is reduced, we have a lower barrier here and a less energy here, every electron that basically finds this edge will still be swept across. And so the drift current, which is electrons being drifted across and holes being drifted across this way, does not change even though we put forward bias voltage. It's still there. Now, remember, it's small. This drift current is small. It's limited by minority carrier generation, electrons and holes, and the minority carrier populations are very small. And so we'll find out that even though we still have this current, it doesn't really matter, because what happens is our diffusion current changes a ton. Remember, I have all these high concentration of electrons here and tiny electron concentration here, and so if I eliminate this barrier here, this energy barrier, all of a sudden the high concentration of electrons this way will see it'll be easier for them to diffuse across from high concentration to low concentration. We'll look at more in a second in terms of how that changes with voltage. And so what you'll see is when you forward bias the diode, yes, you might have drift current, which is still happening, but the diffusion current will dominate, and diffusion current is in the opposite direction of the drift current. Let's look at reverse bias here. and we'll ask some of the same questions. First, let's look at the depletion region. Now our depletion region has gotten wider. It's grown in width because our voltage is negative voltage to the P side. This is reverse bias, which is adding to the contact potential. So if I have more contact potential, then I have to have more charges to create that contact potential, and my depletion region has to increase in width. Again, the bands have to shift. I put negative voltage here, which moves my bands up, right? And so my Fermi levels no longer line up, and now I've got a huge barrier here. And so let's ask ourselves the same question: how do my drift or diffusion currents change? Well, for the drift current, again, there's no change. Even though the energy barrier is greater and the electric field here is stronger, it's the same story. Electrons thermally generated, it finds its way to the edge, it goes across. And so the amount of electrons getting from here to here doesn't change. Same thing, electron thermally generated here, you get a thermally generated hole. If it's within a diffusion length of the edge of the depletion region, it can fall across to the other side. So again, there's no change in the drift current. However, the diffusion current changes substantially. Now I have a high concentration of electrons like I did before, low concentration on this side, but it is very unlikely you're going to have an electron get energy all the way up to here where it can make it over this barrier by diffusion from high concentration to low. And so what happens is my diffusion current quickly becomes zero. It completely disappears. And so the interesting thing about this is that if you look at this, I only have current left due to drift current when I reverse bias this, and that does not change with voltage. So what we will see for a reverse bias diode is that because my reverse current is limited by the thermal generation rate of electrons and holes within a diffusion length of the depletion region, I will see no dependence on the voltage as I increase reverse bias. It will stay constant. So a question is, could we use this as a temperature sensor and an optical sensor? And the answer is absolutely yes. If I took this same reverse bias diode and I heated it up, I would see more thermal generation of electrons and of holes down here, and I would see more reverse saturation current, and I could use this directly to measure temperature of something. What about an optical sensor? I could have a photon of light come in here, be absorbed, create an electron-hole pair, and that electron-hole pair could be swept to the other sides and collected, and I would see an increase in the reverse saturation current. And so that's how we're going to basically make optical detectors when we get to the optoelectronics portion of this course. So, just a bit of review here. Again, if we have no voltage applied whatsoever, Fermi levels line up, we've got our contact potential, we're at thermal equilibrium, and the drift and the diffusion currents cancel out as they should, because of course this thing's not going to generate current on its own. We forward bias it, the depletion region decreases, reduces my contact potential, this side gets pushed down because of the positive voltage, I have less barrier, I see a huge amount of diffusion of high concentration of electrons this way and high concentration holes this way, and because the electrons are negatively charged, negative charges moving this way is current in this direction, positive charges moving in this direction is current in this direction, so my net is a current flow in this direction for both the electrons and the holes. And again, we can reverse bias this, negative voltage on this side. That negative voltage is adding to the contact potential, so I need to uncover more charges to contribute to that contact potential so the depletion region grows in width. And I can see that here. I basically put negative voltage, my bands go up, I get a larger energy barrier. The energy barrier is so great that diffusion current goes to zero because I can't get electrons with enough energy over here to diffuse, or holes with enough energy here to diffuse across there, and I'm left with just my drift current, which does not change with voltage because it's limited by thermal generation of electrons and thermal generation of holes over here. So here's our ideal diode equation that we're going to develop in the next part, the second part of this. If I have a diode, here's my PN junction, okay, and I look at my current, which is current density times the area. My ideal diode equation is I naught e to the qv over kt minus 1, and my I naught is my reverse saturation current. And so If I look at this, it's pretty simple. If I have a negative voltage, this term disappears, right? And so I have I naught times minus 1, and so it says no matter what negative voltage you put, it quickly goes to I naught. Doesn't change with voltage. That's what the equation says. And when I go to forward bias, I see that this term becomes huge. It will dominate over minus 1. This disappears. And I just see I naught times an increasing exponential, and I get this exponential increase in current as I do forward bias voltage for this. And so as we've talked about before, why does it saturate in reverse bias here? It saturates because it's limited by thermal generation. Why does it cross through 0, 0? Well, we know that if a diode has no voltage applied to it, it's not going to generate current by itself. Why is it exponential in forward bias? We haven't answered that. So, any guesses? Think about that. What else in this course have we looked at that is exponential? If you can answer that question, you'll be able to figure out why this is exponential in forward bias. So, here is why the diode is exponential in forward bias. This is critically important to understand. Okay? So first I'm going to assume there's no smoke, meaning that I'm not blowing this device up, because then I would no longer see exponential type current flow. Meaning I'm going to put biases on this, or voltages on this, that are normal operating levels. And I know that diffusion dominates in forward bias, and I know that I'm still going to have a bit of barrier, okay? So that remains. So I'll get to that in a second. So look at the electron population I have here, and we'll do the holes in a second as well. But here's my electrons. Well, we know when we calculated the electron density, we calculated it based off the density of states function, which went like this, and the Fermi distribution, which went like this. And then we end up with a net curve, which looks something like this for the carrier concentration. Let me erase these real quick so I can use this area here. So, here is my distribution of my concentration of carriers versus increasing energy. And I kind of drew this pictorially here, meaning I have few near the edge. It increases near a maximum a little bit above the conduction band here. So this is the edge of the conduction band. And as I go to higher energies, I get exponentially less and less. So with no voltage, these carriers here are the only ones that could diffuse from high concentration to low over this energy barrier, right? As I increase my voltage, this goes down, right? This side decreases, and my energy barrier becomes less and less. And so as this is going down, it's the same as this going up, right? And so if I look at that, I first started that only these electrons above here could get across. And if I keep moving this down over here, then I can tap into more and more and more of these electrons. And we can see how mathematically that'll show up over here. Here's no voltage, very few electrons already have enough energy to get across. You apply a little bit more positive voltage, bands down this way, which is the same as bands up this way. Now you're tapping into more electrons. You apply more voltage, you tap into more electrons more, and you see that the number of electrons that you can tap into as you increase voltage increases exponentially with voltage because of the Fermi distribution, which we had used to calculate the concentration of carriers in the conduction band. So that is critically important to understand that as I put forward bias voltage, my current goes up exponentially because I am lowering the barrier and tapping into an exponentially increasing number of carriers that have enough energy to get over the barrier and diffuse to the other side. And I have the exact same thing for holes because they have a similar function like this down in the valence band, where I have very few right at the edge. I get a maximum, and then it decreases exponentially with distance. And as I lower this, bring this down, I reduce the barrier, and more holes can diffuse across as well. The reason why I said, by the way, normal forward voltage, meaning no smoke and I'm not blowing this device up, is some of you will notice and say, well, it looks like my current should increase exponentially, but then all of a sudden it should decrease because I have my density of states function coming in here. The point of saying no smoke and normal forward voltage means that when you bias a diode, forward bias a diode, you actually never get anywhere near here. By the time typically you get to here, you have so many electrons going across this that the diode will start to heat up to the point where it can blow up. So you never get to the point where you run out of more electrons that can go across, because this is already biasing the diode. When you get to this point, you're already biasing the diode much more strongly than it can handle thermally, and before it basically turns into a puff of smoke. And so you'll never get to the point where you can start to see that the density of states decreases the available number of electrons. So that's it for this first part. Really make sure you understand those things and can answer these questions, and then in the next part we'll start to basically derive the equation for the diode equation using semiconductor parameters, which we've seen before.